Hey everyone, my name is Christopher Love. Today I'm going to be talking about advances and challenges in thin film photovoltaic technology. I'm going to be going over an introduction and a background, perspective technology, challenges, and at the end we'll summarize everything. So, what is thin film photovoltaic solar cell technology? Is the next generation in solar technology. It is composed of micron thick photon absorbing material layers that are deposited over a flexible substrate. Thin film cells have been well known since the late 1970s when solar calculators powered by a small strip of amorphous silicon appeared on the market. By 2015, solar cells as thin as paper could be manufactured using an industrial printer and flexible printed solar panels could be produced. These printed panels can reach up to 20% power conversion efficiency, and a single strip can produce up to 50 watts per square meter. The term thin film solar panels refers to the fact that these types of solar panels use a much thinner level of photovoltaic material than the traditional monocrystalline or multicrystalline solar panels. These layers of active materials are only about 10 nanometers thick compared to the 200 to 300 nanometer layers for crystalline silicon cells. So the single biggest difference between the thin film and traditional solar cells is the thin flexible pairing of layers and the photovoltaic material, which contribute to its flexibility. They also differ in efficiencies and costs. Currently, the crystalline silicon solar cells are the most common solar cells in use mainly because crystalline silicon is stable. It delivers efficiencies in the range of 15 to 25%, and it relies on established process technologies. And in general, it has proven to be reliable. Since crystalline silicon is actually a poor absorber of light, it means that the cells need to be thick and rigid, which explains why the panels are a lot thicker. Thin film technology has always been cheaper but less efficient than conventional crystalline silicon technology. However, it has significantly improved over the years. A basic crystalline silicon cell consists of 6 fundamental layers. A transparent adhesive holds a protective glass cover over the anti-reflective coating that ensures all of the light filters through to the silicon crystalline layers. Like semiconductor technology, an N-type layer sandwiches against a P-type layer, and the entire package is held together with 2 electrical contacts, positive on top and negative below. Not too different than the crystalline silicon components, thin film solar cells consist of about 6 layers as well. In this case, a transparent coating covers the anti-reflective layer. This is followed by the P and N type materials, which are then followed by contact plate and substrate. There are 3 primary types of solar cells that encompass the thin film solar cell market, and they are amorphous silicon, cadmium telluride, and copper indium gallium selenide. So the first one to talk about is amorphous silicon. It is the oldest and most mature type of thin film to produce solar power. This is likely because silicon was already being used in its crystalline form to produce the more traditional panels, and silicon's electrical properties were well understood. Amorphous silicon is the non-crystalline form of silicon. It is the most well-developed of the thin film technologies, having been on the market for more than 15 years. It is widely used in pocket calculators, but it's also powers private homes and other buildings. While traditional crystalline silicon achieves a yield of about 18%, amorphous solar cells yield about 8 to 10%, with a best research or theoretical cell efficiency of 14%. Some advantages of this technology, unlike crystalline silicon, the amorphous silicon version actually has a very high solar absorption rate, which makes very thin layers of the material possible. Additionally, amorphous silicon is relatively abundant, non-toxic, and inexpensive, hence why it quickly became the first thin film method to break the mainstream. The principal advantage of amorphous silicon solar cells is that they have lower manufacturing costs, which makes these cells very cost competitive. Another major advantage of this type of technology is greater resistance to heat. According to a 4-year National Renewable Energy Laboratory study, it was observed that amorphous silicon PV modules actually experience higher results as temperature increases. Another advantage, the development process of amorphous silicon solar panels also renders them much less susceptible to breakage during transport and installation. Some disadvantages of this one is because of its relatively low efficiency, you will mostly only see this method used in small scale, flexible power packs and electronics like calculators. Also, the expected lifetime of amorphous cells is shorter than the lifetime of crystalline cells. How much shorter is difficult to determine, especially as the technology continues to evolve. They are estimated to have a life expectancy of about 25 years or so. So the next one is cadmium telluride. Solar technology based on cadmium telluride is now the second most popular PV technology in the world, sitting at around 5% of total market share and 43% of thin film market. This can be contributed to the fact that manufacturing of this process is cheaper and quicker than comparable silicon-based methods, and recent leaps in efficiency have prompted more mainstream adoption. Additionally, cadmium telluride has a best research cell efficiency of 22.1% and best solar module efficiency of 16%. Some advantages of this technology is ease of manufacturing, it's low cost, and the fact that cadmium is abundant is a huge advantage. Cadmium telluride panels are also highly adaptable to hot, humid weather and low light when compared to traditional cells. This means that they work best in the areas with the most sun and are able to be used in areas that up until now were less than ideal. Some disadvantages of this technology: they have a much lower efficiency than traditional solar cells. Um, Tellurium is not abundant, and cadmium by itself is a very toxic substance that can accumulate in the food chain, much like mercury. Early results show that cadmium can leach from the compound over time in landfills. Fortunately, proper handling and disposal methods will negate much of the potential concern. So the third one to talk about is copper indium gallium selenide. This type of solar cell is another popular type of semiconductor used to create thin film applications. The CIGS method is currently more popular in Europe and Japan, but there are manufacturers all over the world making use of this technique to take advantage of its environmentally safe materials and peak efficiency potential. Currently, CIGS has a best research efficiency of 22.6% and best cell module efficiency of 14.5%. Some advantages of this technology: um, one, it's environmentally friendly in terms of materials used. The materials used also allow it to have the highest potential efficiency of any of the thin film technologies. And like cadmium telluride panels, CIGS solar cell panels show a better resistance to heat than silicon-based solar panels. Consequently, this method has great potential for long life applications due to the lack of significant degradation over time. Some disadvantages: like all thin film solar panels, CIGS panels are not as efficient as crystalline silicon solar cells. Additionally, the cost of manufacturing is higher. So this is a chart by the National Renewable Energy Laboratory, which maintains a plot of compiled values of highest confirmed conversion efficiencies for research cells over a range of technologies. There are 5 different families for semiconductors. We have multi-junction cells, single junction gallium arsenide cells, crystalline silicon cells, thin film technologies, and emerging PV technologies. So, in an ongoing effort to find solar technology that is both environmentally friendly as well as manufactured using abundant materials, the copper zinc tin sulfur method was discovered. This method is very similar to CIGS in terms of properties and methods of fabrication, but its efficiency is still very low. Some advantages of this technology is, as mentioned before, it's made up of earth abundant elements like copper, zinc, tin, and sulfur. This means that the compound is both environmentally friendly and could ultimately become quite cheap because of the material cost. Some disadvantages: it's still in the early stages of development, and to be more commercially viable, higher efficiencies are required. It would need to hit around 20% efficiency before it could become competitive among its peers. But this complicated, still fascinating material is not yet fully understood. Its microstructural and electronic properties depend in a complex manner on its fabrication processes. This explains why a major part of the research efforts during the last 10 years is focused on further understanding thin film silicon material properties and growth. So some key challenges with this technology are higher cell efficiency, element volatility, acquiring a better understanding of the material, and synthesizing a high quality CZTS thin film without any traces of impurities. So to sum it all up, this presentation hopefully provided some insight into the emerging field of thin film photovoltaic technology, along with some of the semiconductor compounds being researched to improve solar cell efficiency. Although the copper zinc tin sulfur solar cell technology is still in its early stage of research, it remains one of the most prospective technologies in thin film photovoltaics. More research will need to be conducted to generate a higher cell efficiency, acquire a better understanding of the electrical characteristics, and generally make copper, zinc, tin, sulfur more viable. Thank you for listening.